Okay, so now that we've looked at both series and parallel circuits, we're going to take the two and combine them in what we can call complex circuits. So this is a circuit that involves multiple parts. It could have multiple series circuits and multiple parallel circuits or components within one overall circuit. Okay, so it's a combination of both. Um, so we have one shown here. So in this example, we have our one path, so we see it's parallel because we can follow our one path through. So our one path takes us through here, so we pass through R2, then out through R1 and back. So here's one circuit or one loop, and we have our second one, which passes through R4, through R3, and then out through R1 and back. Okay, so we can see in our second loop here, so we have a parallel, so R2, this path, is parallel with this other path here. Okay, the current can travel through both separately, but we also see that within this second branch, we have R3 and R4, which are both in series. So how do we solve something like this? And there's a few steps you can do. Step one is look at your circuit. If you have any resistors that are in series, calculate what we call the equivalent resistance, and then draw a new circuit. So I'll show you this in a second, but that's step one. So get everything that's in series solved first. Then solve anything that you can solve with resistors in parallel. Calculate the new equivalent resistance, draw the circuit again. And essentially you just repeat these steps over and over until you have a simple circuit, which is just like a series with one resistor or parallel with just two resistors, one on either path. So let's take a closer look at this example here and break it down some. Okay, so here it is. So consider this following complex circuit. So the first thing we're going to do is we have some resistors in series. So we can simplify this circuit by finding what we're going to call resistor 3, 4. Okay, so that's the equivalent of these two together. Since they're in series, we add resistor 3 plus resistor 4, and that's how we would solve for this. So we then take this and we redraw it. So you see this one, which currently has two in series, is now redrawn with just one resistor on this path, which we call 3, 4, and the total current of this, or total resistance of this, is the two added together. Okay, next we do a similar one except for parallel. So now we have to simplify it because we have this parallel path, or these two parallel paths. So let's get to a simple circuit by combining those. So we'll combine resistor 2 and resistor 3, 4. And to do this, remember, since it's parallel, it's going to be 1 over the total, which is resistor 2, 3, 4, is equal to 1 over resistor 2 plus 1 over resistor 3, 4. So we would add those and then solve for the resistance 2, 3, 4. Again, redraw our equivalent circuit. So now we just have everything on one path. And now it's easy to calculate the total resistance because we just have one path that is in series. So the total is going to be resistor 1 plus resistor 2, 3, 4. Okay, these can take a little bit of practice to get used to because you are trying to figure out which resistors to deal with first, but it will come with time. So let's throw some numbers into one of these and look at a particular example similar to this one. So here we go. Example 3. So find the total current leaving the battery in the circuit below. So we have our total voltage here, okay, that's coming out of the battery. So that's our total voltage. And we have three resistors on two different paths. So we'll call this resistor 1, 2, and 3 to make things simple. So before we can find the total current, let's recall some of our formulas here. So using Ohm's law, V equals IR, IT times RT, we can rearrange this. So the total current would be equal to the total voltage, which we have, over the total resistance, which we do not have yet, right? But we can calculate the total resistance by combining these together to make the simplest equivalent circuit. So let's start with the combinations. First, we combine anything that's in series. So that's resistors 2 and 3 here. So we can find resistor 2, 3 by adding together our 15 ohms and our 8 ohms to give us a total of 23 ohms. Okay, so that's resistor 2, 3. Now we're going to redraw the circuit and replace those two resistors with the equivalent resistor, which would be one of 23 ohms. Okay, but we still can't calculate our total current yet because we still have two resistors. So now we have to combine our parallel resistors. Now this, because it's the last two, is going to give us our total resistance. So 1 over RT is equal to 1 over R1 plus 1 over R2, 3. And we fill in our values, so we have 1 over 10 plus 1 over 23. Just to make things simple, I'm going to convert that to a decimal, which is approximately 0.1435. And then to get R, remember anytime we're dealing with parallel, it's 1 over our resistance. So we have to invert this. So take the other side and flip it. So it's 1 over 0.1453, giving us a total resistance of 6.97 ohms. So that's our entire resistance of the circuit. So now we have our equivalent circuit, right, with our voltage of 6.0 volts and our total resistance of 6.97 ohms. Now that we have our total for both, we can calculate our total current. It's equal to VT over RT, or 6 over 6.97, giving us a total current of 0.86 amps. Okay, so a couple of rules to go along with these, which we call Kirchhoff's rules. Rule number 1, okay, at any junction point, so I'm going to go back for a second. What's a junction point? So this is a junction point. Okay, incoming into this junction point, we have the total current. Outgoing, we have the current on path 1 this way and the current on path 2, 3 this way. Okay, so here's our junction. Total current comes in, current 1 and current 2, 3 go out. Kirchhoff's first rule says that at any junction point, the sum of all the currents entering the junction must be equal to the sum of the currents leaving the junction. So in that previous example, I'll flip back again for a second. That means that the current entering the junction point must be equal to the sum of the currents exiting the junction point. Okay, so we can use this rule to help us calculate the currents along each path. The second rule is the sum of the changes in potential around any closed path of a circuit must be 0. So if we go back again, what that's saying, I'll switch colors here so we can see a bit better. With that saying, if we take this path here, right, we have a total of 6 volts, which means this resistor must use 6 volts. If we take our other path here, a separate individual path, this means since our total is 6 volts, it's only passing through one resistor, so this resistor has to use 6 volts. Okay, so that's Kirchhoff's second law. These two laws can be used to help us solve more information about these complex circuits. So let's go back to the same problem we just did. Okay, so our example here, but we're going to now break down and look for the potential difference across each resistor and the current in each branch. So what we're trying to find here, okay, I'll write down a list. Here's the stuff we know. We know that the total voltage is 6 volts. We know the total current, because we calculated that in the previous part for this question, is 0.86 amps. And what we're looking for, we want to find V1, V2, and V3. And we want to find the current coming in here. So we want to find I1, and we want to find I2, 3. So we're trying to find the potential difference across each resistor, as well as the current in each branch for the complex circuit. Okay, so let's start with current 1. So the voltage here, V1, okay, we know that since this is 6 volts, okay, is our total, it's passing through, here's one branch. So since it's going through this branch according to Kirchhoff's law, since it's only passing through one resistor, that means V1 must be equal to also 6.0 volts. R1 is 10 ohms. So we can use these two to solve for our current in branch 1. 6.0 over 10. Okay, and this gives us 0.60 amps traveling through branch 1. So that's our current for branch 1. Now using Kirchhoff's laws again, we know that the total current entering this junction has to be equal to the currents leaving, so equals I1 plus I23. So this means that we have 0.886 is equal to 0.60 plus I23, and we can solve I for the other branch. I23 is equal to 0.26. I have an eraser here. There it is. 0.26 amps. Since this branch, this I23 branch, since these are in series, if you remember our rules for series circuits, the current is the same in both, which means the current for resistor 3 is equal to 0.26, as well as the current for resistor 2 is also 0.26, since they are both in series. So the last step to this problem then is just calculating our voltage 2 and our voltage 3. For both, we're just using Ohm's law. Okay, so we take V2 is equal to I2 times R2. We have our R2 is 15. Our I2 is 0.26. Multiplying those together gives us 3.9 volts. And V3, doing a similar fashion, multiplying I3 by R3 gives us 2.1 volts. Oh, and I think I'm forgetting one. We didn't calculate V1. We have I1. Oh no, V1 is 6. Sorry, we did calculate V1. And if you look, these two being in series, remember we said the voltage passing through this branch must be equal to the total voltage. Well, if we add 3.9 plus 2.1, it gives us our total voltage of 6. So we know that we do have the correct values here. Okay, and this brings us to an end on circuits. So again, these complex ones can get, well, fairly complex, which is why that's what they're named. But try a few. Make sure you practice these to get the hang of simplifying to make the equivalent circuits and equivalent resistances in each.